Okay, so the last talk of the morning is by Jaco on Generalized LLM magnons.
Thank you, Kostas. Before I start, I'd just like to thank the organizers for what has been a really great workshop for me so far. Firstly, for organizing it, of course, and secondly, for giving me the opportunity to present some of our recent work. So for those of you that don't know me, I'm a postdoc at the University of Utrecht, and I'd like to present some work that I've done in collaboration with Robert and Koch and Link Kim, who's also a postdoc at that. So I'm going to be discussing generalized LLM magnons. It'll become clear exactly what the problem is that we're studying and why it's interesting as we progress through the motivation and background. It's pretty nondescript sections that I have over here, but I essentially plan in section 2 to discuss the gauge theory part of the problem and the string theory part of the problem, and to conclude with some discussion at the end. So the context of the problem is the alias-CFT correspondence, which I think most of you are familiar with, but just for the sake of completeness, it's basically just the conjecture duality between the string theory on alias 5 cross S5 and n is equal to 4 super-Yang moles in 4 dimensions. Specifically, what the duality says is that to each string theory configuration, there should be an operator in the n is equal to 4 super-Yang moles gauge theory, and the energies should be matched with the dimensions of these operators. And though there is no explicit proof, it does pass a multitude of non-trivial checks for its validity. And there's good reason to believe that this is the case. But essentially what we're going to try to do is look at a certain class of operators, match their energies, and make some statements about, make some statements about these operators that I think are quite surprising. So just a bit of a refresher. When we consider these operators, we're thinking of complex n by n valued matrix fields, x, y, and z, and their complex conjugates. And they can also be their fermionic counterparts, and we essentially build gauge invariant operators out of these. I think the ones that are really well known are these single trace operators. So let's say that I have two kinds of fields, z and y, and I build this single trace consisting of a very large number of order square root n of fields. And the reason this is this is quite well known is because this is a very elegant map to a spin chain. And a spin chain that's been shown to be integrable. So how does the map work? Well, you just think of the z as an upspin and the y's, which are the impurities, as downspins. And it's a very elegant map that takes you there. And the Hamiltonian of the spin chain is the dilatation operator in the gauge theory side. And so here's just an explicit construction of a way you can add momenta to these impurities in the spin chain. That's why they're called magnons. Here I basically sum over the position of the first impurity, L1, and the second impurity, L2, and I have a complex phase in front with weight P1 and P2, and I associate with the momentum of these guys. Right. Now, as I said, the single trace operators you typically find in the context of these order square root n operators. But of course, there are many more operators that you can construct. Ones that go like order n, and ones that goes like order n squared. The order square root n ones you can think of as due to strings. The order n ones due to branes. The order n squared ones, you're stacking in so many branes that you can no longer ignore the back reaction onto alias 5 cross S5 in the two picture. And these are really due to new geometries, which I will describe in more detail shortly. But the reason that once you go to these really big operators, the trace operators is no longer a good basis for it. It's not an orthogonal basis. And what you typically use here is that the 2-point function is diagonal for order square root n in the large n limit. But the moment that you consider these bigger guys, this is no longer the case, and a better basis needs to be used to deal with these. And the basis you can use for this are these Schur Polynomials. So it's a basis that's orthogonal for all values of n and for any of these operators that you could put together. And let me just give an example of what I mean with these. And I'm going to consider the half PPS operator. So I only take one of these complex fields. And what you can see here is that I've got n z's, and they're contracted with a specific permutation that I have in mind. I sum over all permutations, and I weight these different guys with what's called a character of the symmetric. And well, the character is determined by a Young diagram of in boxes, and you can pick any Young diagram you like, and if you take two of these guys, their 2-point function, it'll only non-zero if it's the same Young diagram. In that sense, it's an informal basis. Just to mix up the notation a little bit, what you will sometimes see is that instead of writing out this whole chain of z's I have over there, I'll sometimes just use the shorthand notation where I've added the permutation operator that I have in mind inside the trace. And so the way that these characters are computed, I just want to give a bit of a flavor of how that is done. So what you do is you take your Young diagram and you turn this into, well, you write down every possible pattern that you can. So fill out from numbers 1 to n, the order in which I take boxes out of this Young diagram to leave a valid Young diagram at each step. And this is a pattern. And then you take this permutation operator, split it up into adjacent permutations. And when this acts on a pattern, then you're basically going to get two terms. One that's just the pattern itself, weighted with 1 over the difference of the weights of the two boxes, where they're located in the diagram. And another term with the same pattern, but with those indices swapped and the different weight associated with these. Now, the one thing I just want to point out is that note that when the boxes are really far away from each other, then this first term is going to disappear. And I'm only going to be left with a swap pattern at the end. This is the only bit that's going to be important for us in the little while. As I said, it's a basis. So for example, there's a map between the trace operators that we know really well and the Schur polynomials. So here I've taken just a very simple example, trace e to the 3, and it can be written as that combination of Schur polynomials that I have in mind. And they are orthogonal. And another reason that they're particularly useful for our case is that there's a really simple map between Young diagrams with all the n-squared boxes and the so-called LLM geometries. Now what are they? They're half BPS geometries that are asymptotically ADS5 cross S5. And this is essentially the formula that you can write down for them. And you can see there are various factors over here, and there's definitions for these factors in terms of different variables. But the thing to take away here is that there's a single function, z, that determines every quantity in the LLM geometry. So if you give me z, then I uniquely construct the LLM geometry corresponding to that function. And furthermore, z satisfies a Laplace equation. So if you give me the boundary condition, some boundary condition for z, this uniquely determines z, which in turn uniquely determines the LLM geometry that you're considering. And a particularly useful boundary condition to use, or to classify them according to, is a boundary condition that y is equal to 0. And when y is 0, then you see that the factors in front of the 3 spheres tend to go to 0. But the regularity requires that, well, not both of them go to 0, only the one. And this means that either e to the g goes to infinity, or e to the minus g goes to infinity, which means that z goes to plus or minus a half. So if you consider the y is equal to 0 plane, and you color it in with regions of plus a half and minus a half, each different coloring on this plane gives you a new LLM geometry, and this is a useful way to classify them. And there's a very simple map between this boundary condition for z and Young diagrams, which I just want to illustrate with a simple example. So think of this as a big Young diagram that I have over here with n-squared boxes. Then, the way I can move along this is, so it's a representation of un, so you must think of it as n down here. I move up in 1 boxes, then this n1 is going to pick up in the boundary condition as the area of the middle circle, proportional to it. Then I'm going to move n1 to the right, that's the next white region, that's where z is equal to plus a half. And then this last bit is again this black region on the outside, and that's going to have an area proportional to n2. And this is this map between the Young diagrams and this boundary condition for the LLM geometry. So if you will, the map between Young diagrams and LLM geometries. Okay. And as you can see, it's a very elegant map in the Schur polynomial language. That's why it's very useful to use, or one of the reasons it's very useful to use. Now, we became interested in them quite a while back already. And what we studied were localized excitations with the Schur polynomials. So what we have in mind is Young diagrams that are order n squared, but that have order 1 corners. So not just these are the examples that I use throughout the notes here, but you can really think of it as any number of steps that you will. As long as the number of steps is sort of 1, and they're well separated, these are the diagrams that we're interested in. And it's because you get a notion of localization of excitations on these backgrounds. But now, how do I construct it explicitly? In the Schur polynomial language, again, it's a very convenient thing to do. Suppose I have this as my background, and I want to say, take an excitation of this form and attach it to this outer corner over here. So in the ideal string picture, what I have in mind is string excitation stretching just along the outer ring over there. Then the idea is, in the Schur polynomial language, you literally take the two Young diagrams and stick them together like Lego pieces in this way. And then you see that the operator representing the background plus the excitation is now just this combined Schur polynomial that I have in mind over here. All right.
Sure. Is this excitation a string or a giant graviton or what?
Oh, so
how long is this?
So I've obviously, for the sake of space, you must think of this as, you know, all the inboxes or the inboxes, and this one, you know, also all the
Order 1 or order n?
So I haven't specified that yet.
Okay.
So this is just, you know, whatever you want to attach. We're going to be thinking about strings, so this will be an order square root n, and it won't be half BBS. It'll have impurities in it, but it's. I think the discussion of the restricted Schur polynomials just becomes a bit technical. The main idea is the following, and it's just that if you give me the Schur polynomials, I can think about these localized excitations in a very natural way in the language. As I said, we are interested in studying string excitations on the background, and that means that we're going to consider operators that go like square root n, that have a lot of z's and some y's in it representing impurities that will be dual to strings. Now, what we did in this paper is study the one-loop dilatation operator on these operators, and so think about, here's my trace that I have in mind, bunch of z's and some impurities spacing in between them, and yeah, as you can see the label saying that I've attached it in some way to a background. And there are two types of terms that you get from acting with this dilatation operator. That is the derivatives with respect to z and y. And it's basically terms that just act on the trace, so just act on the excitation on top of the background, and then also terms that start mixing the background z fields and the fields inside the trace. And what we managed to show is that the terms of the second type scale like, I say they're 1 over n, but it's really 1 over the separation between, you know, where on the background does the z field come from and where's my excitation sitting. But because our Young diagram is, you know, consists of well-separated corners, these all scale like 1 over n, so in the large n limit, I only need to consider the terms of form 1. So the dilatation operator is still only acting on the trace. Now what you find is that, at least at the one loop level, shown explicitly, that all that happens with it is that the action of the one loop dilatation operator is absolutely identical for any one of the corners. The only difference is that you need to rescale n wherever it appears. So in the Toff coupling, or you know, for example, you just need to rescale n with no longer n, but the weight of the box where you're attaching this excitation, and that is the only difference between them. So at Newton, we wrote this down initially before that this is good evidence that, you know, beyond the large n limit, this is a notion of localizing these excitations. So even though it's only shown explicitly for the one loop case, you know, this should be a statement that possibly holds to all ones. And well, if you're skeptical, then you'd probably throw the following argument in my direction and say, oh, operators were interested in have a, you know, extended symmetry. I have this background Z, so this reduces the symmetry of Superman moles from SO6 down to a residual SU22 square. And there's this beautiful argument by Beiser that shows that in this representation that he has in mind, where you've got the impurities and you've got these supercharges transforming between the different kinds of impurities, the symmetries really determine a lot of things for you. Among others, it determines the exact dispersion relation of these operators. So in other words, the one loop result is already contained in here. And in addition, it also contains or captures the kinematic part of the scattering matrix of two of these magnons. So the only thing it doesn't determine is this overall phase, the dynamical phase of the S matrix. And well, what happens if I study the one-loop dilatation operator? You find that there's no contribution from the dynamical phase to the S matrix at one loop. So in other words, you could say that, well, the argument that we've made, you know, as I say, if you're skeptical, it's just that, you know, you've just reproduced the kinematic known results in this way. And, you know, to really show it, you need to go to higher loops or to, you know, strong coupling. And that's exactly what I intend to do in this talk. Again, study the same kinds of excitations and more generalized versions of them, and show that this notion that the only thing that happens is a rescaling of the coupling still holds. Okay. So what we studied were operators, or what we studied before, are operators attached to a single corner of this Young diagram. But you can study more general kinds of excitations and have operators that stretch between these different edges. And the idea to create them is, well, you know how to create localized excitations. So add a trace at corner 1, a trace at corner 2, and then act with an operator like this that's going to break open the trace at corner 2 and break open the one at corner 1 and tie them back together with one another. And thus create the excitation. There are a few ways to do it, but the correct way turns out to be the following. So here I have the trace at corner 1 and the trace at corner 2, as I want. And this is the operator that I need to act with. So I want to take y's and add them back into the positions of v and w. And the reason this is important is that I can't use a y here, because if I use the y there, then the dilatation operator is going to start mixing them up in different ways, and you can get y's that, you know, don't sit where you want them to sit at the end. By putting this you know, different impurity in there, that produces for you the correct operating unit. And the dilatation operator acting on these are going to have the following kinds of terms. The dilatation operator only acting at H1, where I've added this trace, one at H2, and then one because you have these y's that stretch between the two edges. There's also the possibility to swap fields between the different groups. And then, as before, terms that mix these trace operators and the background fields. But again, following the arguments that we had before, these are suppressed. And you know, if you have well-separated corners, they don't contribute.
But you only have 3 scalars, right? So V and W, are they conjugate scalars, or what could they be as?
So you shouldn't think of V and W as fields in you know, in sub-Yang theory. They're in a sense placeholder fields for you know, and you're going to substitute it with you know, one of the fields that you're interested in.
So they're going to become Y's eventually.
Yeah. In terms of the construction, there's nothing prohibiting you from doing that. You can add as many restriction labels to the Schur polynomial as you want, even ones that don't correspond to fields actually in sub-Yang. What you're going to find is that you know, there's going to be a difference between the y's at corner 1 and the y's that were replaced by a V or W and the ones that weren't, but it just ends up being an extra restriction label in the Schur polynomial. So there's nothing prohibiting you from doing that. The final operator you get is just one that consists of z's and y's, and that's a perfectly fine you know, operator at the end. All right. So as I said, what we want to now do is study what is the action of the two-loop dilatation operator on this. And well, I'm going to consider the most general case, and I'm going to, for now, be interested in 2 adjacent impurities somewhere in the spin chain. And you can see that I did exactly the same thing I did before. Again, sum over their position, so I actually didn't include their position, but L1 corresponds to the Y and L2 to the X. But you can also consider the case where they are both Y's or they're both X's. Doesn't really matter, but this is the most technically challenging one that you're going to encounter. And the subscript I have refers to different edges. So I have a bunch of excitations sitting at corner 1, and then I have this middle corner where they both meet, corner 0, and then they stretch again to another corner, corner 2, in the Young diagram. And I don't assume anything about their ordering, and I don't assume any equality between them. You can afterwards substitute any ordering or equality that you want, and we're going to get different results based on that. Now, what we need to do is study the two-loop dilatation operator, and fortunately, it turns out that It's still a single trace operator. There's no fields mixing in from the background again, and I can still just think of this as some generalized spin chain. And this issue2 free spin chain has been studied before. I've shown you the one-loop dilatation operator. Well, that's the term coming before this, and these are new ones. That's, take the two-loop or the three-loop and the two-loop and the three-loop, I mean, sorry. But this is, as I said, this is for, think of the trace operator living in ABS, or the trace operator on the trivial background, or in, the strings in ABS5 plus S5. This is this is the dilatation operator acting on those. Alpha and beta refer to fermionic fields, A, B, and C to bosonic ones. And you can see there are various swaps that take place. So take this term, for example, that's going to swap A and B. And this term over here is going to take, no, this is not the one I'm interested in. This last one over here is going to take field C and swap it past, two spaces, which you can expect from the two-loop dilatation operator. And just a footnote here that if you're considering, three fields next to each other that are the same, these terms all vanish. You can show that point. Now, all we need to do is...
So is the reason for 2/3 that it's two-loop closed, or is it, why are you focusing on this U2/3?
So, I'm trying to think. So the previous one that we had, so you have the...
Because before you were in this U2 sector, X's and Y's.
Yes, that's correct.
But now you went to two loops, but you also went to, so why couldn't you have stayed in the U2 sector?
Oh, you could. We're just considering a more general possibility. So the impurities, I don't assume to be the same, which we can do. And it's going to be important when we study the symmetries. In a second, that's going to become clear.
Okay, so it would be too trivial to do two loops. Just in the U2 sector, you would not get
exactly
structures.
Exactly. So in order to extract information about the phase, I need two different impurities in the chain. Exactly. So all we need to do is, these are all the kinds of terms that the dilatation operator acting on these spin chains are going to produce for you. In our case, we're just going to have to adjust the weights of these. And the different weights is because, as I said here at the top, different regions correspond to different corners on the Young diagram. If you're sitting in a different corner, you need to rescale in. This means I need to rescale the coupling. So the coupling in the region 1, region 0, and region 2 is going to be different. But they can all be accounted for and given the appropriate weights. A simple way that works for most of the diagrams that I've shown previously is, let's take the following term where I've got y and x, y stretching from 1 to 0, and now it's adjacent to x, stretching from 0 to 2, and then I've got a z field sitting at corner 2, and it's going to get swapped around so that z is now sitting to the left of y, so that it's now sitting on corner 1. Then all you need to do is look at the weights sitting in between these fields. So in the first one I've got R0, so that's the one that I need to keep in mind. Between x and z I've got R2. Between z and y on the bottom row, well, I think these two should be short. This should be R1, and then the last one I've got again R0. And this is the appropriate weight to give this interaction term that I have over there. So using this recipe, the ones you just need to be careful of are these terms, but you can get the right weights if you just study what interactions are really included in that term, and you can get all of them correctly. So then you get a bunch of equations. So I write down the spin chain where I've got a y and an x as my impurities, x and y, the fermionic ones, and you make the following ansatz for the solution. I know that it's very similar to plane waves, but then I've got this extra term over here, and the rationale is that I know that if these plane waves that move past each other, then it's just going to be the kinematics, energy conservation, momentum conservation that determines everything for me. But if they're adjacent to one another, now I need to be a bit more careful, and I can potentially get something different. And you do get something different in this case. But the point is just that it's just a change in our ansatz. You plug it in, and then you just solve for the various equations that you can.
So you find that you need these contact terms?
Yes.
For consistency.
So they're non-zero. But note that if I just study the one loop operator, then they disappear. So I need to drop that order. So it's just because I'm considering the two loops that they appear. And the interaction taking me from bosons to fermions also only appears at this loop order. So that's why I need to include decimal nonsense as well. If you were just to stick to one loop, you'd throw away these two terms in your nonsense as well, and you'd be able to solve it. But this is what I take as input, along with these equations that determine the final momenta and energies for me. Well, just the final momenta really, the energies are determined in terms of the momenta. And now you just solve the expression, the spin chain Hamiltonian I heard done before, generalized with the appropriate weights, must give me back, energy times the same state. And I'm not going to write down the solutions. You can put it into Mathematica. It cranks for maybe 20 minutes, and then produces expressions for you. I don't think they're very enlightening on themselves, but the following results I do want to emphasize further. You get the following expression for the energy. So I get the one loop result, appropriate result over here, and two loop result also contained in there. And you can see it's the sum of two energies, energy for the one magnon and energy for the second magnon, and this matches the exact result that we know should hold. Then what you can also do is take this ratio of these coefficients. So in my ansatz I had A and B. Take this ansatz for the coefficients and then compare that with the S matrix that you get just from the symmetry argument. Just take the bit that takes two bosonic fields to a symmetric combination of bosonic fields, and the one that takes two bosonic fields to an antisymmetric combination of bosonic fields, those two terms, take their ratio, and that should be equal to that. The reason that you can do this comparison is because by taking this ratio, the dynamical phase cancels out. So I just use the kinematic part, which I know completely, to determine this. And it's a consistency check for the equations that I've written down and solved. And you can do this check and it works out perfectly for any value of R0, R1, and R2. Now, of course, the case that we are mostly interested in is R1 is equal to R2 equal to R0. That one I'm sticking to a single edge on the Young diagram. And if you do this, you see that everything is just rescaled. So I just get this, N needs to be rescaled with the effective N of the relevant corner that you're sitting at. And this is, now keep in mind, I've taken this ratio of these to just give you the kinematic factor, that matches. But A and B also have the same property, meaning that the contribution coming from the dynamical phase also has this rescale. So, and this is a very good low coupling check that not only at one loop level, which just took the kinematic part of this matrix, but also the contribution of two loops coming from the dynamical phase has to match. Or has to, show this rescaling behavior if I stick to a single corner of this Young diagram. So at two loops, they're still localized, and you still see this effect. Let me just see how I'm doing my time. Okay. So what we've done now is the two loops. So it's a weak coupling check of the conjecture. And what we now just want to turn to is the strong coupling limit. So strong coupling, so I'm going to consider the dual strings and study their energies and see what comes out at the end. So you'll remember this LLM background that I wrote down before. So this is a dual geometry that these excitations are running on. Those of you that are observant will notice that I made a slight coordinate change. I think it's phi goes to phi plus t or something like that, but it's still the same geometry. It's so nothing funny going on there. But you take this background, this is the TR phi subspace, and you study the number go-to action, taking this as input. And what you can show is that for any LLM geometry, so independent of my choices for V and H, this still comes out as a solution. So this combination, R is equal to C over cos phi plus T. And this corresponds exactly to the known giant magnon solutions in S phi plus S phi. And well, you can compute the energies and angular momentum. And if I compute the combination E minus G or minus J, I get exactly the strong coupling result for the exact energies that I wrote down before. Notice though that here I have the angular extent of the magnon, and that should be identified with the momentum, or the momentum of the magnon. And this is the standard way that this is done. But once you've done that identification, there's an exact matching between these two. But again, this is just confirming the kinematic result that we already know. So can we do a little bit more? And we can do the following. So we're going to study how finite size corrections of these magnon excitations. So before I had, this is an ansatz that R is just a function of phi plus t. And what's happening here is that I have so many z fields, all the square root n z fields, they end to infinity, and these z's drag down the endpoints of the magnon to a geodesic. And this is then, the relation to velocity at those endpoints. If I don't have infinite number of z's, a large but finite number of z's, I can expect the z's not to drag it down all the way to the geodesic, just above it. And this shows up as a change in the angular component of my ansatz over there. So I'm thinking of kappa as a number that's smaller than 1, just a little smaller than 1. Alright, so this is my ansatz for what the solutions are. The convenient choice for the worldsheet coordinates is t is kappa tau, phi is equal to sigma minus tau, so that R is just a function of sigma. And the way you can think about this is that these excitations are ones that retain their shape as a function of sigma, and they're then moving at a certain velocity in time around the, around the 2 sphere. All right, so you can plug these into the equations of motion coming from the Mandelstam action, and you can show that they're solved by this over here for general LLM geometry. Note that the functions h and v appear explicitly in this. So in the worldsheet description of these solutions, those functions do play a role over there. So if there's still a matching, it is a significantly more sophisticated check. And if kappa goes to 1, then as you'd expect, the dependencies just drop out, as we've seen before.
What those kappas are? Oh, it's
yeah, so it's this component over there. When kappa goes to 1, then I expect to get the infinite size giant magnon back again. And as I commented, that's independent of these functions h and v that you have, and that's exactly what you see in these finite size solutions over here. Now, I said the equations of motion are solved by this. Of course, this is just the derivative of R, so in order to do the computation...
Why is the kappa that you multiply the time, the worldsheet time, is that the same kappa as the one you put in?
Yes, exactly. So that's the same kappa.
So they have to be the same for Schur constraints, or something makes them be the same?
Do you mean for the different LLM geometries?
No, just your answers for the string.
Mm-hmm.
Kappa appears in 2 places, which in the a priori look independent.
Oh,
places.
I see. Yeah. So the second line here is just a choice that I make, a convenient choice, so that R is just a function of a single variable. So nothing more mysterious other than that. The key in the ansatz is really the one at the top over there. From there, you can then make almost any choice for sigma and tau that you want, and this turns out to be a convenient choice because now R is just a function of a single variable. Anyway, this is the solution that you get, and I can't solve for R exactly. For that, I need more information about h and v. So I'm going to do the following: just do a coordinate transformation where all my conserved quantities E and J, and also the angular extent, which would be just the integral of sigma for these magnons. I'm just going to make a coordinate transformation from sigma to R. And if you give me a function of sigma, then this is going to be the rule at the end. So I have a sigma minimum and a sigma maximum, and that's the total extent. And corresponding to these will be some values for R. But notice that what I have here is the 2 endpoints for this string. So something just off the geodesic, the endpoint 1 and endpoint 2. And they meet somewhere in the middle at some value for R. And so this is going to be something that's going to be floating around in your final solutions, but you can then set that relative to the central charges, which we're going to do in a second. So notice that, and the boundary conditions I'm going to impose is the following: that R mid is just equal to C, so that's where the numerator vanishes, so that's where the derivative is 0. The endpoints are going to be any choices for which the derivative of R goes to infinity, so the 0 coming from the denominator over there. And notice that if I pick a different LLM geometries, I can get many different possibilities for the inputs. So you can pick any 2 roots that you want. This corresponds to the freedom that you have to make it in any corner of the young diagram. To do the computation, it's
But I thought your string isn't at the same. Are there the inputs at the same radius, or?
so we're going to specialize to that case towards the end. But you can do the computation in general and do it for any two inputs. So you can think of in that circles that I had that specify the boundary condition, you can have it end at any one of those circles and stretching to the endpoint of any one of the circles. And those are the two different radii. Of course, it's just off that, so that minus a small exponential piece. But the point being that you can choose any of those inputs that you want, and you can do the computation for any of them. And we're going to specialize to the case where it's at a single edge right after that, yes. Now, what's useful to do is the following, just coordinate change, and just take this constant k that I had and just redefine it in terms of a new constant. And then I'm also just going to plug in some knowledge that I know of V. V corresponds to a sum of poles of all possible points where I can have an endpoint. And I'm just going to single out a special endpoint where I know it's ending. And the rest of it has to vanish because it's a different endpoint. When Z is equal to 0, I'm at the endpoint. And so I'm going to multiply this with an overall Z. And that has to vanish. And this is the makeup of my LLM geometry. But that's the only input that I'm going to use in the following computations. And so now that you've done this, you made a coordinate transformation to Z. The convenience of this choice is that independent of LLM geometry, and independent of LLM geometry, your integrals are always of this form. I integrate from this number f up to 1 over Z. And then, of course, the conserved charge could be energy, could be J, could be P. And these are different integrals that you now need to try and solve. If I have time, I just want to comment quickly on this. Okay, I don't really have time to comment on this, but it's just a technical question. How do I evaluate these kinds of integrals where I have an f dependent sitting in the integrand as well as the bounds of the integral? But it's one that you can address and solve. And then you can just do those integrals and put them together. The answers you get are still going to be in terms of this constant C and F. So C and F are going to appear in your final answer. But then what you do is you get answer for E, for J, and for P. And then you just take the leading order contributions and solve for F and C in terms of the conserved charges. So this is the final result that you get. If I take a combination E minus J, I get the leading order piece that I should mention that now I've just specialized to the case where they have the same edge, but you can solve them in general, which I'll show in the next slide. The point is that I get the leading order piece that I should, plus then this extra piece over here, that's the finite size correction of these methods. And the thing to just note here is that here I've got the tooth coupling, and I've just got this rescaling factor appearing in front of them. This is the appropriate factor that you need, and it also appears next to the coupling of the beam. Now, people that know this result will say, but what should appear in the exponent over here is just J0, and not some J0 minus some other constant V. But if you take a bit of a closer look at these expressions, the point is that J0 for general LLM geometry takes contributions from every single edge on the in the background, and this is not a local quantity, in other words. The local quantity is J0 minus V, which gives me this, which is something that is just localized at the single edge. So when I think of J0, which is the length of these trace operators that I have in mind, as excitations on this background, then this is the local quantity that I should associate with the length of the operators. In other words, once I have that done, then there's exact matching, and you can just see this rescaling appearing if they're stuck at a single edge, exactly as predicted. Now, I said that there is a general result. Here's the general result. A bit more messy, obviously, but the only thing to take away here is that if they're stretching between different edges, you don't get this simple rescaling of the coupling. It's a more involved answer that you get in the end. And here at the bottom, I've just included an example. Here I've still got F undetermined, and this is the leading contribution for J. And now I just need to invert this relation to solve for F in terms of J, plug it back into my expression to get the final answer. All right. Now, the reason that these finite size corrections are important for the statement about the dynamical phase of the S matrix is because the finite size corrections for these magnons should correspond to the so-called Schur corrections. What the Schur corrections take, again, I'm not going to go through the details of the computation, but it takes as input the S matrix that you've computed, or the S matrix for the scattering of these two. And this has a kinematic part, which you already know, and that we can just plug in, but it's also going to get a contribution from the dynamical overall phase, which we don't know a priori. But the point is, because the finite size corrections just have the simple rescaling, this means that the contribution coming from the dynamical phase also just has to have this simple rescaling. And this is strong evidence that in strong coupling, the dynamical phase, is just simply again rescaled. The only difference between attaching it to corner 1 and corner 2 is that there needs to be a rescaling of the coupling strength. Now, the reason that we find this particularly interesting is that this implies that if I study the dynamics of these excitations at any corner of these Young diagrams, or in the trivial background, so I study string on AD as 5 cross S5, or just these single trace operators with no background operator, then the point is that the dynamics, the action of the dilatation operator, should be completely equivalent. And in particular, we know that these single trace operators, or the strings living on R class S2, form an integrable subset of n is equal to 4 sub n mods. And if the dynamics are equivalent, this means that on these Young diagrams with order 1 corners, this means that the excitation, the stringing excitations are attached to them, should also, in other words, form an integrable subset of the theory. And this is significant because it's an integrable subset far away from the planar limit of the theory. I'm considering operators, background plus excitation, with scale like order n squared, and yet, if this conjecture is correct, and it seems so from the weak and strong coupling results, then this means that these operators should span an integrable subset of n is equal to 4 sub n mods. So, as I said, it's operators are equivalent. It's good evidence, and it means that these should span an integrable subset of the theory. I'm running out of a bit of time as I anticipated, but I just want to say that we can extend these as well and study dionic magnons in this LLM backgrounds. So what you can do is, instead of studying excitations on the T, R, and phi subspace, you can add another angular direction, you get another conserved charge, another angular momentum associated with that. And you can write down the solutions again for any background. So for the infinite size dionic giant magnon, this is the appropriate ansatz, and you could get the appropriate charges out. Notice that in this case, unlike the giant magnon case, the worldsheet description is sensitive to the specifics of the LLM geometry. The worldsheet description is sensitive, but the conserved charges themselves, when you compute EJ, J2, they're insensitive to the specifics of the LLM geometry. And I didn't include the finite size corrections to them, unfortunately, but you can also study finite size corrections. You get a very similar, setup to what we had before. So I could solve for the derivatives of functions in terms of sigma, and you can plug that into your conserved charges, do those integrals with exactly the same methods, get some answers out. Much longer expressions, but if you restrict to dionic giant magnons stretching between, not stretching between different edges, but localized at the same edge, you get, again, results that are consistent with the prediction. I just have this rescaling of the coupling, which is all further evidence that things are indeed working in this way. So, what we're planning to do with this in the future is, one of the first questions that I think will come up is, if these are really integrable subsectors, I should be able to construct a lax pair of these, and how can one go about doing this? Now, this is probably a pretty difficult problem because the point here is that when integrability is studied on AD as 5 cross S5, there's only one edge for me to attach excitations to, and those excitations are form an integrable subsector. And so in other words, in a certain sense, integrability is inherited from properties of spacetime. In this case, that's not the case. So as I showed, there are operators that I can build on these LLM geometries that don't have integrability. They don't even satisfy the Yang-Baxter relation. They don't have elastic scattering. So the general excitation of this background will not give you an integrable subsector. It's only once you combine this with the boundary condition that they stretch between a single edge that this should be the case. And if we can construct that, the question is, what can we do with that? I think one of the natural things would be to write out scattering solutions. So I've studied a single macron now and the Lucia corrections, which incorporate roughly the scattering of a particle and an antiparticle. But how would you write out the general scattering solution? You'd expect that the world sheet description would again be sensitive to the specifics of the LLM geometry. So again, should be a tough problem, but if the system is integrable, it should be doable. And then, of course, we've written down some results for the energies of these magnon states stretching between different edges. And can we extract more information from that? Perhaps information relating to the overall dynamical phase of these. That's an open question. And also go on to studying different geometries. So the ones that we had were LLM geometries, that had order 1 edges. I could add excitations. Can you have ones that have order n edges? That's a really different beast. And the question would be if one could use the Schur Polynomial methods to study those as well. I think that's all I wanted to say. So thank you for your attention. And I just want to thank the All Foundation for their funding to support this research. Thank you.
Any questions? So in the case with the different edges, what's the gauge theory Young tableau description?
So you'd still have
you're attaching several.
So it's basically these operators that we constructed before. So these were these trace operators stretching between different edges. So that includes find the correct slide for it. So it will basically be these operators over here. Well, I've attached this to the first corner, that to the second corner, and together they form some, closed trace spin chain stretching over different edges. And these are operators. But that plus the background.
And you can match these to the result you have on the graphic side? Okay. Even though there's not this overall rescaling, but you can still match something?
Absolutely, yeah. So the point is that you can study the two-loop dilatation operator. And let me just get that expression for you over here. So this is the exact result that you'd expect from symmetries. But you can match that with the two-loop dilatation operator answer. This one, do I have that at the bottom? Oh, there we go. It's this one at the top. So that's what you get from the gauge theory studying the two-loop dilatation operator, and then also from the string theory. This is the result that you get. Exactly. So and they both match the exact result as you would expect.
One question.
So if I understand correctly, is that your operators were order root n?
So the excitation is order root n, but the background fields are order n squared. So the total operator that you construct is still an order n squared object. But the point is that you have this notion of localizability in these LLM backgrounds because the corners are well separated. And that means that whenever the dilatation operator acts, I can ignore the action mixing the background with the excitation. And I can just focus on the dilatation operator on the excitation. And that's why you can roughly expect them to be equivalent. I can always reduce it to just the dilatation operator acting on this order square root n thing, which is well known, and that's why I turn out this one.
So what kind of diagrams do you found in that case?
I'm not sure I follow it.
So what I'm asking is whether you're founding planar or non-planar diagrams.
Well, we don't. I think we can discuss it afterwards. It's probably in this somewhere. So in the computations here, you don't end up with, I don't think you really some diagrams. You just have these terms, the spin chain Hamiltonian, and these you need to tweak a bit. But you know, that's basically computation. But I'm sure underlying you'll really some diagrams, but we can discuss afterwards.
Okay, if no more questions, let's thank Jaco again.